Traditional link-state routing protocols, like OSPF, rely on a simple premise. Every node must maintain a complete, constantly updated map of the entire network topology. To build this map, nodes continuously broadcast link-state updates to all of their neighbors. In a wired environment with dedicated cables, this continuous chatter works, but mobile ad hoc networks, or MANETs, rely on the wireless channel, and at the MAC layer, the wireless medium is inherently shared. When multiple radios in close proximity transmit in the same frequency band at the same time, their signals physically overlap. This interference causes packet collisions, forcing constant retransmissions and severely degrading the throughput of the channel. Now look at what happens if we apply standard link-state broadcasting to a dense cluster of mobile nodes. Node A sends an update. Every immediate neighbor receives it and obediently rebroadcasts it to their neighbors, who do exactly the same. The identical packet is duplicated exponentially across the same geographic space, drowning out all useful data traffic. This cascading failure is known as a broadcast storm. Without strict rules governing exactly who is allowed to transmit, continuous proactive flooding will paralyze a wireless ad hoc network. This slide outlines the Optimized Link-State Routing Protocol, or OLSR. It is a proactive, table-driven routing protocol, meaning it is designed to maintain the stable topology mapping of a standard link-state algorithm. But to survive the physical constraints of a shared wireless medium, OLSR implements a structural optimization known as selective flooding. The protocol establishes a strict rule: not every node is allowed to participate in a broadcast. Only a highly specific subset of nodes, designated as multi-point relays, or MPRs, are granted permission to retransmit control messages. By revoking the default broadcast rights from the majority of the network, OLSR forces each individual device to perform a local calculation that drastically reduces the volume of redundant transmissions network-wide. To see how that subset of relays is chosen, we have to look at the network from the perspective of a single unit. Let's isolate node S, surrounded by its immediate one-hop neighbors, and the next ring out, its two-hop neighbors. Node S discovers its immediate surroundings by broadcasting a local hello message. Every one-hop neighbor does the same, allowing S to compile a list of the nodes it can reach directly. OLSR modifies the hello payload. As the slide indicates, every node attaches its verified one-hop neighbors to outgoing hello messages. By parsing these lists, Node S builds a perfect matrix of its one-hop and two-hop surroundings. There is a specific parameter for this matrix. As noted here, the link between a node and any potential relay must be verified as bidirectional. Unidirectional links are discarded. Through this localized hello exchange, Node S maps a precise two-hop radius around itself, entirely through local gossip, and without generating a single network-wide broadcast. Now, Node S must solve a specific geometric puzzle. It needs to determine the minimum number of one-hop neighbors required to establish a route to every single node in that two-hop ring. These highlighted outer nodes are the targets. Node S evaluates the connections. If a single one-hop neighbor connects to 3 targets, it has high utility. If another one-hop neighbor connects only to targets already covered by the first, it is redundant. S calculates the optimal configuration, isolating the exact subset of transmitters that provides complete access with the least overlap. This exact mathematical subset of one-hop neighbors becomes Node S's multi-point relays. As the document specifies, the defining requirement of the chosen MPR set is absolute coverage. Every node 2 hops away must be reachable through at least one of the selected relays. The MPR selection is a classic set cover algorithm. By mathematically guaranteeing maximum 2-hop reach with a minimum number of transmitters, Node S prepares its immediate neighborhood for optimal routing. Let's put this into practice. Node S determines it is time to alert the network to a topology change, so it generates and broadcasts a control packet. Physically, the radio wave propagates uniformly. Every node within the one-hop radius receives the transmission. As stated here, neighbor nodes not explicitly chosen as MPRs silently drop the broadcast. Even chosen MPRs check their MPR selector table, a list of nodes that nominated them. They only forward the packet if the sender is on that list. This dual verification, knowing you are an MPR and confirming the sender actually selected you, strips out all overlapping rogue transmissions at the source. When every individual node applies this logic simultaneously, the behavior of the entire network shifts. Look at a standard flood versus an OLSR flood under load. On the left, naive flooding creates a dense, chaotic overlap of radio interference, choking the channel. On the right, the selective flood uses the MPR backbone. The control message ripples outward through precise, mathematically isolated transmission radii. Because OLSR manages this routing data proactively, the topology maps are always current. When a node actually needs to send a data packet, there is zero route discovery latency. The path is already computed. This specific balance of low routing latency and strictly controlled bandwidth overhead is why the protocol documentation concludes it is highly suitable for large and dense networks. By moving the complexity to local computation, OLSR tames the physical chaos of the wireless medium, turning an ad hoc scattering of radios into a mathematically optimized routing backbone.